I'm Eleanor Rieffel. I'm a senior research scientist and the lead of the Quantum Artificial Intelligence Lab at the NASA Ames Research Center. I'll be talking today about utilizing NISQ devices for evaluating quantum algorithms and would like to thank my wonderful team and our amazing sponsors for their support for this work. Thank you. The first question I often get asked is, why is NASA interested in quantum computing? And it's important to remember that NASA is constantly confronted with massively challenging computational problems. This means that for a long time, NASA has invested in computational resources. So, for example, NASA has one of the fastest supercomputers in the world. These challenges are in space, they're also in aeronautics, the first A in NASA, in earth sciences, and the like. Back in 2011, NASA Ames Research Center decided to invest in a small group to look at the potential for quantum computation to enable more ambitious and safer NASA missions of the future. It's a really exciting time now to be in this field. Quantum supremacy has been achieved. What this means is that these tiny chips that people have built that are quantum computers, even though they're very primitive and noisy at the moment, are able to do a certain type of computation that's not possible in a reasonable amount of time on even the largest supercomputers. We were really excited to be part of the Google NASA ORNL collaboration on this work. But it's important to realize that useful quantum supremacy hasn't been achieved yet. So processors are currently too small and noisy to be useful for solving practical problems, with a possible exception that if you're particularly interested in the application of certified random number generation, then you're in luck. But most other problems require much more in the way of computational power and fidelity. So what should we do with these still limited but very exciting devices? So one is to continue hardware and noise investigations, but another is algorithmic investigations, and that's what I'm going to concentrate on here. And these insights from quantum algorithms feed into the next generation of hardware, and the hardware constraints feed into the algorithms. What's particularly exciting at this point is that we can now explore algorithms, quantum algorithms, in a way that we couldn't before. We're able to run things on these processors. And a big question is, what should we be running? And early targets that we and many others are looking at are in optimization, in sampling and machine learning, and in simulation of quantum systems. And I just want to mention at this point that there are both general purpose quantum processors and also special purpose quantum processors that may run just one type of algorithm, like quantum annealers, or are targeted at one particular type of application. And this heterogeneous ecosystem is very important for these explorations. The status of quantum algorithms is that there are some really exciting, provable advantages for, depending on how you count, a few dozen quantum algorithms. There are also a lot of limitations on quantum computations known, but for the vast majority of problems, we do not know what the best algorithm is, what the quantum advantage will be for those. And at this stage of the technology, that is not surprising. The best classical algorithm is not known for most of these problems. And for many of the hardest computational problems, such as machine learning and optimization, there are ongoing heuristic developments within classical cases where you just try things out and see what happens. That's why there are machine learning competitions, SAT competitions, planning and scheduling competitions. And until recently, quantum computing hasn't been able to do this because we haven't been able to run. But with quantum hardware reaching the point where it can get past what classical computers can simulate, we can experiment with quantum heuristics, and that will significantly broaden the applications of quantum computing, just as classical heuristics are applied in a wide variety of areas where we don't have provable best algorithms classically. So we're looking particularly at areas of optimization, of machine learning, also of quantum simulation. And I'll emphasize optimization here, but also we'll discuss some related work on sampling as well. So optimization problems are frequently solved by classical heuristics, but they are also often slower or don't find as good solutions as one would like. And machine learning is also dominated by heuristics, with efficient sampling often being a bottleneck. Before going on, I want to point out that there are diverse optimization goals. Sometimes one wants exact optimization with the best possible state with a guarantee. Sometimes one wants approximate optimization where the configuration is guaranteed to be within a certain ratio of the best. Other times one's happy with just good heuristics, which run fast but don't have these guarantees. Sometimes one may want multiple solutions. For example, if one doesn't know all of the parameters for the optimization and want to choose from a bunch of good cases going forward. There are similarly a bunch of different sampling goals for machine learning. So we're interested in quantum optimization algorithms. There are a lot of longer term algorithms, but I will concentrate on a couple of the nearer term algorithms. These got their inspiration initially from adiabatic quantum computing, but they all have the same elements of having a cost function based operator that allows you to do, quote, phase separation in the quantum space that enables you to take into account problem structure, and then a driver or mixing operator that allows exploration. So quantum annealing has this sort of evolution that takes both these terms, but I will first concentrate on a more recent algorithm, QuAIL, that alternates between the applications of cost function based terms and these mixer or exploration terms, p times. And how long you apply those terms are the parameters for this algorithm. So one of the things that my group did was we generalized or extended early quantum approximation quantum approximate optimization algorithms to a more general quantum alternating operator ansatz that isn't just for approximate optimization, but can be used also for exact optimization or sampling. And it takes the basic framework of this approximate optimization algorithm, which is this iteration between these two types of operations. And there were some very exciting early results showing that if you do this infinitely many times with the right parameters, you always converge to the optimum. And on the opposite side, if you just alternate once, this can be provably hard to sample from the output of these circuits and briefly beat the approximation ratio of on a problem max E3 lin 2 before inspiring a better classical algorithm. Later results included a new algorithm we came up with for quantum unstructured search that achieves the same query complexity but within this framework and potentially more implementable. What inspired our work on the quantum alternating operator ansatz was both problem structure and also constraints that came from compiling these algorithms to near-term hardware. So we wanted to be able to encode constraints in a way where instead of putting them in a penalty function, which is done for quantum annealing very frequently, because that's what one has control over on current annealers, instead we wanted to restrict the exploration to the actual feasible subspace where the hard constraints are met and then optimize within that space. But when doing that, this mixer that allows the exploration within just that feasible subspace was a bit more complicated. And so implementing it was hard on these near-term devices. It took a lot of circuit depth. So instead, we realized that there was no reason why you had to have that form. Instead, you could get a mixer that was closer to the hardware and did this sort of exploration, but where instead of having one global Hamiltonian that encoded how you were doing the exploration, you could have local Hamiltonians that correspond to your single and 2-qubit gates and build mixers out of that. And so that was a generalization here. And you want to start in an initial state, which is in that feasible subspace. So let me walk you through an example here. So for example, the MaxK colorable subgraph problem, you're given a graph and K colors, and you want to find a color assignment maximizing the number of properly colored edges, namely edges where the endpoints are assigned different colors. Now, there are a bunch of ways you can encode this problem, but one way is the quote one-hot encoding, where you have variables corresponding to a vertex and a color. And that variable is 1 if that vertex is colored with that color and 0 otherwise. Then the optimization cost is easy to write down. It's just the number of edges, subtracting off the miscolored ones. But we need to avoid invalid colorings where a given vertex is assigned multiple colors or no color at all. And that second category is particularly important because the way we've defined the cost function, if we didn't color anything at all, then we wouldn't have to subtract off bad edges. But that, of course, is not a valid coloring. So we want to require that for each of these vertices, exactly one of these variables is 1, because that corresponds to assigning exactly one color to a given vertex. But you'll notice that if you do the standard exploration of just flipping a bit, you'll immediately get to the stage where either you've assigned a vertex 2 colors or no colors. So we want to do a better mixer that keeps the evolution in this feasible subspace of a single color to each vertex. And so instead of doing a bit flip mixer, we're going to do a swap mixer, or equivalently a XY mixer, that allows you to swap the values of these variables corresponding to colors for a given vertex. And there are a bunch of different ways one can do it. One can order all the colors and swap just between adjacent ones. One could have swap operations between all and basically have a complete mixer. And there are trade-offs here between that and also how you do the initial state choice that may give you higher probability of success in theory, but you want to keep the circuit depth small on these NISQ devices. So for example, for initial state choice, you could choose something really bad, which is assigning all colors red, which is feasible but very far from optimal. Or you could try a superposition of all feasible states, but that's much harder to implement. And so there's a trade-off here, and also for the mixers in terms of implementation on these devices. I'll also mention that because these terms don't always commute, you need to think about ordering, and there's also different possible orderings here. And so you can partition these mixers into different sets of qubits depending on the ordering. So I won't say more about there, but you can look at our paper for that idea. So what I want to mention is that we've done numerical explorations that have confirmed that having these mixers that maintain the evolution in the feasible subspace is advantageous. In fact, the probability of staying in that feasible subspace shrinks exponentially with n. We've also looked at trade-offs in the depth for the mixers and the initial state, and very recently we were able to show that even though noise can possibly take you out of the feasible subspace, it's still an advantage to take this XY mixer and this feasible subspace evolution under noise. So I want to turn now to QAOA parameter setting basics, because this is really critical to getting the algorithm to work. So in the original paper, they showed that for constant number of iterations p, there's a polynomial time classical algorithm. But unfortunately, as you increase p, this increases exponentially. There are a bunch of different approaches to parameter setting. If you're lucky, you can find them analytically, like was done for the Grover case. In other cases, you may be able to use a classical algorithm that estimates the expectation value and then update the parameters. And in other cases, you may need to run on the actual quantum processor or a simulator and update the parameters that way. And there's been a lot of work here on parameter setting. And I want to mention some observations. So, first of all, people often worry about turning a optimization problem into a different sort of optimization problem of finding these parameters. And I want to emphasize that we only need to find good parameters. We don't need to find the best parameters here. We need to find ones that have good scaling. Further, most people get concerned about parameters getting stuck in local minima and not being able to get out of it. But actually, a bigger problem is often getting stuck in featureless plateaus where there's no information as to how to get to a better parameter range. And so you just spend a huge amount of time basically making no improvement at all, wandering around this flat plateau. And so that's something to really watch out for here. While for Grover's unstructured search problem, we were able to find a simple periodic parameters analytically, for a really trivial problem of MaxK on the ring, finding good parameters is harder than expected. One of the really exciting things is that there's more connections between quantum annealing schedules and QAOA parameter setting. So there's been a number of recent papers that draw connections between these, where in easier problems, you often see adiabatic schedules, but for harder problems, one sees diabatic schedules. And so I encourage people to look further at these connections. And that is one reason why we're still very excited about doing quantum annealing work. We have recent work that extended earlier work we did showing that just a simple schedule change of inserting a pause at an appropriate time can give orders of magnitude improvement in the performance. And recently, we've been able to show that this improves the time to solution on embedded instances, which are what you see in application problems, and that again, you find a consistent region in which the pausing helps. So recent paper in June. And we've also been continuing work on compiling to realistic hardware, which is really critical to these experiments. In the interest of time, I won't go over that because I really want to emphasize that it's really critical to compare with the best classical algorithms, and that there's a lot of great work where there's physics-inspired classical algorithms. And it's really important to compare apples to apples here and compare appropriately tailored or not tailored approaches to similar work with whether they're tailored to a certain problem or not. We have state-of-the-art implementations of a lot of these physics-inspired algorithms, which have been very helpful in our benchmarking of our results. And another very important case is doing simulation, including high-performance computing simulations of quantum circuits. And we're very excited to have some open source code here available for people to use. And I'd like to conclude with an inspirational historical perspective. So back in 1972, the director of NASA Ames at the time, Hans Mark, brought the ILIAC 4, the first massively parallel computer, to NASA Ames. It had a 50 megaplot peak, and that's not a typo, a 64-bit processors. And a challenge at the time was finding good problems and algorithms to show off what massively parallel computing would eventually be able to do. And I'll just end by saying that if in quantum computing we can have even a fraction of the impact that massively parallel computing has had, we'll have a major impact on the future of technology and a variety of applications to come. Thank you very much.